¿Podemos empezar?
Podemos.
Well, thank you. Welcome to the new session of the Chilean Probability Seminar. We have the pleasure today to have with us Laurent Miclo, who is visiting the CMM during this month, who is in a Toulouse School of Economics, who will talk today about fraudulent stochastic algorithms. Thank you.
Thank you for the invitation, and also not only on the economics department, but also on mathematics.
Yes. Sorry.
Otherwise, they will cut. No. So I work with several, based on several papers, and with several collaborators, Michel Benaïm, Jérôme Bolte, who is often here, I've been told, and Stéphane Villeneuve. So what the subject? This is the plane I will try to follow. I will remind you the problem. I think that everybody knows the problem of global optimization. We'll see the result, and because it's interesting to see the proof, not the details of the proof, of course, but some principles of the proof. And after that, I will come back to some other algorithm and why they are related to this one. In fact, the story we started with that, with Bolte and Villeneuve, and then something happened, but the link between the two for the moment is heuristic. So we'll see that later. So, global optimization, you have a function. Well, we will assume that the function is nice. It's smooth, everything. It's defined on I will take a Riemannian manifold, a compact Riemannian manifold. So I can differentiate, but if you don't like Riemannian manifold, you should just consider the torus to some power. So it will be the same, but the setting is the more natural one is here. We will assume it is connected, and we will write little m for the dimension. And I said no problem of differentiability, even if everything could be considered more generally than forces. So what we want to know is, we want to find points which are globally minimizing my function. Since I am on a compact, of course, there are some points here, and the function is continuous. So how to do that? There is a general heuristic, it's not a heuristic, it's a way to find such point with a stochastic algorithm we call the simulated annealing. I will present it now. This is the more general one because you don't need assumption on you can use it. The convergence is very slow, but at least you have you know that in infinite time, furthermore, infinite time you will be close to you. But you can make a quantitative statement. But when U is particular, there are other ways to optimize a global optimization algorithm, especially if it is convex. But convex, this is not our point. I don't like from convex because since I'm used to work either on finite state space or compact Riemannian manifold, I don't know what it means convex because what does it mean to be convex? I think there is a generalization using optimal transport of understanding what is really convex, not just the function is a x plus n minus y is smaller than that. I think there is something more conceptual to find, but just to say that the convex, I don't know. So we will not be interested in convex function here. Also, when you are in Rd, for instance, and the function u is a polynomial, you can use what's called the moment method. But this is particular function. Even if, well, we tell me, well, polynomial function is almost all function because you can approximate, etc. But, well, on our compact manifold, what would be the meaning of polynomial? But it's true, they could do an extension, for example. On a compact Riemannian manifold, you have a natural Laplacian. You can consider the eigenvalue. There will be only a denumerable set of eigenvalue because you are compact, and you can consider the eigenfunction associated, and you can consider polynomial in this eigen function, which will play the role of usual polynomial. But here, let's go there. So we recall what's the simulated ending, but everybody knows about the stochastic calculus. Yes, stochastic calculus. So everybody understands this sentence. Yeah. So you have your ZT, which will be evolving in your compact manifold. It will be submitted first to the Brownian motion. What is a Brownian motion? On a Riemannian manifold, it's a Markov process whose generator is given by half the Laplace. And so, well, it's a little, this is heuristic, but if we are in the torus, it makes sense because it will be in a torus, a Brownian motion as a torus. You just take a Brownian usual Brownian motion on R, and in the torus you just take R and you put it like that. Then you just make it periodical. So it's clear to understand what's the Brownian motion on the second. And if you have a power product of circles, it's clear also because one on each of the coordinates. So here it makes sense to push by a Brownian motion. And furthermore, we have a gradient descent according to you, the function you want to minimize, but we will multiply by a constant, which is called the inverse temperature. And we can find certain inverse temperature schemes such that this process will have the property that if you take any neighborhood of the global minima, then you will end up in probability, because it's not true almost surely, you will end up in probability to be close to the global minimum. And this, I could say, I didn't write it, but here, the scheme you need to take, it will be like that. It will be logarithmic. Well, here you can replace one by whatever you want. And there is a condition, k should be large enough, and we know what is the critical value, such that if I consider such an evolution for the inverse temperature, then this property that I will find in probability the global minima is true. But be careful, in general, almost surely convergence doesn't hold. For instance, here I should say, so here there is a critical value, C. Maybe I will make my usual picture. This is your function U, and C, what is C, is the largest eight of a well which doesn't contain the global minima, which is here. But when you do, so you take k larger than that, so k will be something like that, it's larger than that. And if you put here this length k, in fact, all these points are recurrent for the process. So you have no convergence almost surely, but the process, of course, since in probability will be mainly here in the neighborhood, but sometimes you will do that, and we each has if you fix a time, there will be a time after that where you will be here. So it's not. It's almost here. This is an example where you have convergence in probability, but not convergence in almost. So. And here, there was only one global minima, but of course, there can be other global minima, but be careful. Yeah, if here, I have the one. Here, as soon as this is the largest, because here, if I have another global minima as the same value, this length should be smaller than this one. That you can do. And you will concentrate on these 2 points with a certain probability, positive probability of each one. So, yeah. So, but this, to put in practice this algorithm, you don't need to know the global minima, the value, the minimal value of U. You don't need it because you use each time you just use the gradient. So you don't care what is it. So I call the product algorithm, stochastic algorithm, which will use this value, this minimal value. You can say, that's why I call it fraudulent. You are cheating a little because to know what is the minimal value of U is more or less to know at least one global minima for you. But this is not always true. But even if it's true, this kind of algorithm can be interesting because assume you have one global minima, and you want to know all the other one. So this kind of algorithm are interesting to do that, from one to go to another one. And there are also, since now you have to say I'm not doing at all machine learning, but if you want some money, you should say I'm not doing. So some people from machine learning tell me, oh, no, but there are functions where you don't you know the minimal value, for example, 0, but you don't know where are the global minima. This is over-parametrized. You want to no, maybe I should not enter that, but this machine learning, you want, the problem is you want to find a functions such that, and here you put parameter, and you want such that this is 0. Here, say for example, you have a sum of this kind of stuff. This is your, how do you say, your learning sample. And you have a parameterized function on some theta, and you want to find a theta such that on your learning sample, this is equal to 0. But if you take all the functions, if all the samples, for instance, are different, there is a function which satisfies that. But you don't know which one. And over-parameterized, it means you have too many, this will be a 10. If the set of theta is fit something large, so there will be a function satisfying that. This is a case where you cannot, the global minima is 0, but you don't know where it is, and this algorithm can be used to find them. And the kind of algorithm I will present you appear already as some limit of what they are using in machine learning. And at the end, I will present you an algorithm which is not fraudulent. You don't know the minimal value of U, but you will learn it naturally when the process is evolving. And that's why in some limit, you will get some fraudulent algorithm. So, yeah, maybe I should, yeah. So let's go on and present the algorithm. So what is the algorithm? Now I will make an assumption on you, but we will see how to relax this assumption. So first assume this is a Morse function. So everybody knows what is a Morse function. But it is the simplest function. You look at a point which is a critical point. So what is a critical point? This is a point U. X such that this is the gradient is equal to 0. It could be a local minima, global minima, or some saddle point. So you look at such point and you compute the relation. Well, and you look at the relation. Yeah, I will take. But of course, since I'm was there, and so I won't define exactly well the relation in the Riemannian context can be not well defined. You have to be careful, but at least if you have a point which is critical, you can define the relation at x of u. And this is if you are in my product of torus, this is the one you think of as the matrix of all the second derivative. And this should be non-degenerate, meaning the eigenvalue, this is a symmetric, so you can degeneralize it. Here are some eigenvalue, and none of the eigenvalue should be 0. So if it is true for any x which is critical, the relation doesn't admit 0 as an eigenvalue. This is called a Morse function. But this is a nice, a relatively nice function. And now we consider another evolution. Yeah, the previous one, the simultaneity, was time-inhomogeneous. What I'm doing at time t was depending on my parameter gamma t. No, this is no longer true. This is an homogeneous process. Nevertheless, I have a parameter, but the parameter doesn't depend on time. So again, I follow a gradient descent with this parameter beta. But what's new is that in front of my Brownian motion, I put u. Yes, and since I'm in a fraudulent setting, I assume from now on that the minimal value of u is 0. Because as we know it, up to shift, it doesn't matter. So you see what will happen when I will be close to the global minima. I will follow the gradient, so I go to RE. But here, my Brownian motion, I more or less I switch it off. Not exactly, because it will not be. But I will. The influence of the Brownian motion will be smaller and smaller. And and what's strange, the guy is crazy. Why he's taking beta in R? It should be in R plus, because we don't want to. We work a descent gradient, not an ascent gradient. But it will be interesting to have beta real number. So, especially as a student, we say, but he said there is a solution, but why there is a solution? So don't be afraid. Here, everything is Lipschitz. Why is Lipschitz? Because, well, the gradient of u, of course, is Lipschitz. We are on a compact manifold, so it's Lipschitz. So maybe you could be afraid by the square root, but remember that where is the problem of the square root is in 0. When I'm 0, it means that I'm close to a global minima, and since the assumption of well, you don't even need at worst, when I'm close to 0, this will be of order x squared, because the gradient will be 0. So the function evolve. This is the Morse. There is a Morse lemma. Say that close to a global minima, in fact, the function is like a square up to some product, etc. So in fact, taking the square root, in fact, you will have a Lipschitz function. Maybe it's not. It will be Lipschitz. So there is no problem. All the coefficients are Lipschitz. There is a solution which is defined for all time. And it is fraudulent because I assume that the minimal of u is 0. So when you work with such process, you are not using, in fact, this description. It's just for you to understand what's happening with the process. We use the generator. So the generator is just the Laplacian IS. That's why I have put a 2 here. Is to remove the Laplacian over 2. So you have the generator of this process, time-homogeneous process. He takes a function, he takes the Laplacian multiplied by the beta, and after that, he takes the gradient of u, and you take the gradient of your function. Okay? And that's all we use each time. This is the way to define the fraud process. Okay. Yeah, what are the results? So now we define a certain value, beta 0, which is a dimension over 2 minus 1. That's why I take also I permitted to beta to be negative, because you see, if m is 1, if I am in the circle, the only compact one is the circle. Here I have something which is negative, which is minus 1/2. And so the theorem now we say, according to where is situated beta with respect to beta 0, we will have two different behavior. But also for beta negative, for instance, when m is equal to 1. So the first result say that if I take beta sufficiently large, so remember, beta sufficiently large, I have a tendency, the gradient descent is quite strong. The larger beta, the descent will be stronger and stronger. So you have more chance to go toward the global minimum. So the result here is quantitative. If I take beta slightly larger than beta 0, so whatever the initial condition, in fact, I will have my process which converge almost surely, and the limit belong to the set of global limits. This is completely different from the simultaneous annealing. Because simultaneous annealing, I think you have one set which is recurrent. And furthermore, well, at least when the dimension is equal to at least 2, any points, any global minima will be attracting the trajectory with the positive probability. Of course, this cannot be true. I should have said something also. I told you, yes, the process is always well defined. So there is one case where we know the behavior. If I start from a global minima, you see, this is 0, this is 0, I will not move. Yeah, because of the Lipschitz. The Lipschitz are 1, 0. So I won't move, but so here I have to be careful when I am in the circle. Assume here, this is the circle. So you have your function and assume that there are several global minima. Here you have 3 global minima, for instance, so your function could be that, and this value, all these 3 values are the same. So of course, if I start something here, I cannot go across such a point, because if I reach this point, I said I will stay at the point. So when you are in the circle, in fact, I change the. Okay. So here I said all the global minima will be attained with a certain probability, but if I start from here at 0, I cannot code that, so I will just visit these 2 global minima, but not this one. So this is the natural statement, but you have to be careful. You will only reach the boundary. Yeah. And of course, all the other ones, they will be 0. Now, there is, this was for beta larger than beta 0, but now what happens when beta is smaller than beta 0? So now the behavior is different. First, there will be no convergence in almost sure convergence, but you will have a convergence in low. So yeah, but now you have to be careful. There will be a convergence towards the global minima, but if I start at the global minima, as I told you, whatever the beta, if I start at one global minima, I will stay at the global minima. So I should start with a distribution not putting weight on the global minima. And in this case, you look at the position at time t, it will converge in low toward the invariant measure of the process. Here you consider as new state space, you consider in your manifold and you remove the global minima. So now it's still a Riemannian manifold, but it's no longer compact because you have removed some points on the global minima. And the point is that if you start here, you will stay in this state space and you will converge toward probability, the invariant probability on T space. And this invariant probability put a weight 0 on the global minima. So you won't see, in fact, the global minima. So you see, it's completely different before. Before I convert to global minima, no, I don't see the global minima. And the threshold is exactly at this beta 0. So in the case of the circle, you converge towards the global minima, even for instance, for beta equal minus 1,4. So you have a volume motion, and you add an ascent of gradient. But nevertheless, the ascent is not sufficient with respect to the slowdown you put in front of the volume motion. Yeah. Yeah, and this was for L1 because the same problem as before. If you have m equal 1, you should consider the connected component. And you have if you start here, you will reach an invariant measure which is supported by Bolte. That we will describe. It's not a mysterious invariant measure. So, well, we can be more precise, but I think it's not so what's important. Where is this two? Don't say the two statement. Here you can consider, you consider a global minima. So you consider the Hessian. The Hessian, if you are at a global minima, the Hessian is a positive infinite matrix. You consider all the eigenvalue, and especially the minimal one, strictly positive one. But after you take also the minimum over all the global minima. Well, I should have said that the set of global minima is finite because we are a compact manifold, and around a global minima, since I am increasing in square, there is a neighborhood where there is nobody else as critical point. And this is sufficient because of compactness to get the finiteness. So once you converge toward this infinite limit, in fact, you converge exponentially fast with a weight which is given by all the minimal of the eigenvalue of the H. So this is the case, of course, where beta is larger than beta 0. If no, see the invariant probability, in fact, it's quite simple. As I said that on a Riemannian manifold, there is a Riemannian probability, compact Riemannian, which is just the invariant measure of the Laplacian. I mean, then, of course, if you met a guy from geometry, you shouldn't say, oh yeah, this is just the invariant measure of the Laplacian, because no, there is a formula using the determinant of local number, but there is formula for geometry people, but for us probabilists, this is the invariant measure of the Laplacian. So I write it like that. And the invariant probability, so for beta, in fact, this probability is invariant whatever beta, except that it will be a probability only if beta is smaller than beta 0. You can make the computation, to see, because, well, when you are far away from the global minima, there is no problem to integrate that this is bounded. The problem is when you are coming closer to the global minima, this will explode when beta is positive, for instance. And this is where they can have mass. And for beta larger than beta 0, in fact, close to the global minima, the mass of this measure is infinite. For any neighborhood of a point, it's infinite. And the criterion, in fact, was that is it a finite measure or not? And if it's finite, we renormalize it to get a one probability. And this is the case for beta smaller than beta 0. So in the case where beta is smaller than beta 0, you have all the usual stuff about the ergodicity. This is, for instance, the ergodicity in almost sure ergodicity. You take a function, which is in L1 of my measure. And if you take this empirical mean in time, you converge towards the probability. You have also the ergodicity in space, meaning that if I look at the speed of convergence towards the global, towards the invariant measure, this is exponentially fast with certain constant, but this is not so nice result because you didn't. You're surprised by that? No, this is usual stuff. This is the main 3D kind of results. But I don't like so much, but since it works. So you have convergence for a certain norm, which is this norm. So in particular, it says that here I'm starting outside the global minimum, but if I'm starting close, you see this will be very small. So you have a bond which is very large. If I start close to the global minimum, the convergence will not be so good. It will still be exponential, but the B, I think, is not a very good. So for B, there is the critical case, exactly beta equal beta 0. Who cares about the critical, but we just succeeded to show that, in fact, if you take any neighborhood of you won't spend a lot of time because this will be you will spend a lot of time around the global minimum, but it's not sufficient to distinguish between the two, the numerical case or the numerical case. This is where you have an invariant measure, which is the case here. But so there's still work to do. So what are the proof? Yes. So I first proved this result, but with a bad beta 0. Meaning I didn't have a beta 0 exactly. I have some bound. I knew that for beta smaller than something, it was this behavior of an invariant probability and convergent invariant. And for larger, I have the result that you have almost shown. But then I presented this talk, well, the previous version of it to Michel, Benaïm. No, we should do more precise. And so we use this policy theory of it's called higher extension and persistence. So persistence corresponds to you have a species, you have a species, and we still be alive for a long time. And this is persistent, and this corresponds to the existence of an invariant measure. The process XT can survive for a long time. But extinction is when you go towards the global, toward extinction for the zero case. So we work and try to apply his result. It was in fact a nice example of where it works. So yeah, there was a nice idea. I didn't know that to understand the behavior near a global minima, in fact, you shouldn't see the global minima as a point. You should explode it into a sphere. You have seen that? No. I will, because I think it's a good idea. So I will. That's why I wanted to present this proof. So we will start, since we want to do something locally, I will present it for you. I take Euclidean space Rn. So I have a function u on Rn, and my critical pointer, I will assume it is y equals 0, but doesn't matter. I take an epsilon sufficiently small. I still assume that u is Morse function. So I can find a small epsilon such that on the ball, except 0 is the unique critical points. And you see, and you should see the function as really as something quadratic, up to renormalizing the axis, but some axis. So first, I will write something very simple. Usually you don't write it. You just you see. We will consider when I'm in this ball, well, except in 0, I will consider its polar decomposition. So this is the norm, and this is angle in some sense, but here I am in Rn. So the angle is a point on the sphere. And now if I have a function which is defined on this ball, I can see it as a function, just using this polar decomposition, as a function of 0 epsilon, which is the norm, and the angle. So yeah, stupid. We are all doing that, except that what we will be doing, we will extend to 0. It means that when at 0 there was only one point, now there will be the point and all the possible directions. 0 will contain the direction, and this will be the trick we will make everything works. So that's why I told you explode the point. You see it, initially it was like that, but then you make a product. So here in 0, well, it doesn't matter what was the theta. No, the theta will matter. So we replace that, in fact, a product, epsilon, to a product and with a sphere of dimension n-1. Yeah. So that's why I use, usually you say, well, I have F. What's the problem?
Sure, I have to change sometimes when right on the board.
I should not run.
No.
I should run from one side to the other. So this is just the polar decomposition, but I give a name to that. I say this my F, which was defined on the ball. Now I see it defined here. And in fact, you rewrite your generator in this in rho in theta. So in general, you have this expression, but you don't make a difference between the previous one. You say, this is the same. But here you have to be more careful because of the case rho equals 0. And in fact, you have you see, here you need good eyes, because there was one with this slanted, which was the initial generator, and make it straight when this is the generator acting in rho and theta. So in rho and theta, the straight one, so you make the computation the usual change of variable, and you get this things. But now, since u is a Morse function at 0, you can make an expansion when rho is yes, the same for the function. I was my usual u, which was something. I know I put it straight. But since they are so close, maybe it's not important if you don't see the difference. But here, this is a real statement. When I let rho go to 0 for the function, I told you it's quadratic. If you divide by rho square, what you should do, in fact, you get a function, and it depends from where you are going to 0. See, here, you have to move. No, here you have your theta. So the limits depend when you go to 0, depend, in fact, in the direction you go toward the theta. And this is divided by this quantity. Go back. What is A? A is the relation at 0. So this is a positive definite, positive definite matrix. And you get that. It's easy computation. You just make a function. But you have the same when you consider the derivative with respect to rho. There is a limit. You know you have to divide by rho. And also, when you take the derivative in theta, you have to divide by rho squared to get a limit. And you get this limit. So yeah, you have to be careful. Here, this is a gradient according to theta, so this is a gradient on the sphere. So, and here, this vector, maybe. So, this vector will be tangent, this is a gradient, it will be tangent to the sphere, because we are working on the sphere. So, elementary computation, but you can believe them second year of university, when you make a change of variable. You get that. So, it follows that but my generator is using all these derivatives. Yeah, but let's forget something. I don't know. This is it follows. Maybe it's, yeah, you also have to expand the Laplace, right? But you take a function, but now the function is also defined in 0. And the function is C2 also in 0 in the direction theta. So it's you take such a function and you let your generator acting at a point, a nice point, rho strictly positive and theta, and you let rho goes to 0. In fact, you get that you get a limit. And the limit is a generator acting on the function restricted with rho equals 0. So, if you want, you have your process here, but in the limit, when you look what is doing on the angle, there is a limit on the angle. And this is given by a generator. So the more you can compute the generator, it's given by this one. So now you have, you have a product in front, but it doesn't. Yes. Remember that this is strictly positive. Theta is an element of the sphere. You take A, theta, and theta, and A is a positive difference. So this is strictly positive. So multiplying a generator by a quantity strictly positive, we know it's just changing, making a change of time. A stochastic change of time, but only a stochastic change of time. And here, what do you have? You have the Laplacian on the sphere. You know, that's why also the Riemannian setting is natural, because here we are considering the Riemann setting on the sphere. So you should know what is the Laplacian on the sphere, which is what. And so there is a second order term. There is also a first order term. We should take the gradient on the sphere and you multiply by a certain function, which is given by that. So when you look only at the angle, when the process is going towards 0, in fact, this angle is almost Markovian and follow this generator. So in general, we like this kind of generator when I am in a Riemannian manifold. I like this to be a gradient. Because if this is a gradient, I know the invariant measure of this system. And if it is not a gradient, first of all, it's if and only if. If it is not a gradient, in fact, you can show that the diffusion is not reversible. The reversibility in this context, when you have a Laplacian plus a drift, it is reversible if and only if the drift is a gradient. But we are lucky. We are lucky because if you make the computation, this is the gradient of this quantity. I take the log of this function, which is everywhere, of theta times the scalar product with a theta. I take the log, it is strictly positive, no problem, and this is the gradient of that. It means that, yes, I should have also said something, a general result about Markov processes. Assume I have a generator, which is a function, positive function, times another generator. So we can go from the invariant measure of one of them to the other one, because the invariant measure will only multiply by your factor. Change the invariant measure by the factor which is input. So here I told you we know the invariant measure because when it is a gradient, it is exponential minus the function which applies the gradient. So for this one, we know the invariant measure, and here we have multiplication by something. So we know the invariant measure, and this is the invariant measure we get. Quite close to the previous one I told you. In fact, the restriction, yeah. So this is the first ingredient we need. Yes, the result of Michel. Yeah, in this setting, you have an half space. Your diffusion is defined here on the half space, and but you want to know here you will make assumption such like that when you go close to that, you have a generator, but you need another assumption, which is the following. And furthermore, I just I read that before coming. I said that there is an assumption missing. So the second ingredient you need is that on you. So here, we're leaving naturally your process, and you want to know if you will go to a limit which one which is here. So we need first that when I look at the generator converge to a generator which was observed. But we need something else. We need a function v defined now not in zero, because the missing assumption which is here is that the limit of v rho theta, say, when rho goes to zero, this should explode. Because this is very important. So the function itself should explode, but if you look at what's called the carré du champ, so when you have a Markov generator, the general definition of the carré du champ is what? You take a function, you take the square, and you let the generator act on it, but you have to remove 2 times v and l acting on v. Why? Because this operation, it kills all the first order terms. Here, if L beta or any general Markov generator was an operator of order 1, differential operator 1, it would be 0. So it kills all, and you just get the second order. It doesn't keep it because it replaces. Yeah, I should have said. If you take the Laplacian, because why it's called the carré du champ, it's in French. A lot of French in that. So if you take the operator, which is the Laplacian, and you consider, but generally you have it's defined in 2 functions. For the guy, the definition is the following: you take the product plus the square, and you remove f and g minus g and f. Maybe here you see because this is 0 if and only if you define that with this operator, then you get So I'm not sure about that. Maybe there is that too. But what you will get is the following. So here maybe there is a 1/2, 2, or 1. The convergence. That's why it's called because if you take f equal g, you take the norm square of the gradient. So the derivation in French. So my function which explode, you should have this correlation which is bounded. So the function explode, but so you should go. So here you go to plus infinity, but in some sense the gradient doesn't explode itself. And I think that's all. No. And furthermore, if you look at the generator at this function, which a priori the function is the generator, you do not apply it to function which explodes. But this should go to a limit, despite the fact that V explodes. And you will call H beta the limit. So H beta is only a function of theta, because we will let it go to 0. Then the criterion for do I converge, do the process converge almost surely toward the boundary, and after it converges toward the boundary, but it doesn't converge to a point. It converges in the steps from Michel. It converges to a process which will follow the generator given there. But the question is, do I converge toward this boundary or not? And the criterion is simple. You integrate with the invariant measure of the process this function which appears as a limit point. And what's surprising, it doesn't depend on, because you can say, oh, it's fine, you're right, because maybe there are several V which satisfies this condition. But whatever the V you get, this positive negativity say that if you are convergent of the limit or not. So this was the result, but now we apply to our case. If I take V, which is the log of rho, well, it's nice, it's exploding. You can compute the generator. It gives you this function. Yes, so what? Yeah, and we use the limit. We know the limit of that. I told you what the limit of that, and rho plus 0 and that. And you get this function here. So now I integrate this function with respect to my invariant measure, but it doesn't matter because you see, this is a positive quantity. What matters, in fact, is this term. And this term, we see that it is positive or negative according to beta larger than beta 0. So this is mainly the idea of the result. So now I will make a picture. Take your. You don't need it from your hand. Okay. Where is I was to take my glasses. Anyway, no. So now I can give you the proof of the convergence, almost sure convergence. On the whiteboard. So this is your manifold. You have several points which are the global minima, and you can make a little ball around each of them, such that, assume we have beta larger than beta 0. So you know that once you are here, by using the result in Rn, once I'm here, I have a chance to converge on motion. But it's not sure. It's not sure because it can go out. But once you go outside this ball, in fact, my process is elliptic, meaning that I will go everywhere. So once I'm here, I know that at some time I will enter the boundary of one of these balls. Here I have a chance to converge. Maybe I won't converge, but still I can go and can re-enter this one, for instance. Each time I enter one of the balls, I have a chance to converge to the center point. So it will end up at least. And that's how you will prove the convergence. What time is it? I have to stop now.
5 minutes.
5 minutes. So very fast. Very fast. Yeah, the most assumption we can, well, we see, but we have not done. Okay, to be honest. No, in 5 minutes it will be difficult to. So there are some. Do you know non-linear Markov processes? Non-linear Markov processes. This is processes which are sometimes they depend on itself where they are to evolve, but they also depend on their whole distribution. And here there is an example of such. Yeah, but it won't be 5 minutes now. So maybe it's better I stop here. You told me we start 5 minutes late and we stop 5 minutes before.
No.
No?
It could be, but still have 5 minutes. So if you want to steal 5 minutes, well, it's
Well, if there is a Chimian way, if someone is interested in the application of this warm algorithm, some algorithm you have a particle, but we go to the limit to get an evolution of the law, which is given by that. And in some limit, we recover the algorithm are collected. So if you are tested, you just come to me since I'm still here for 10 days. And I prefer to respect your tradition.
moving out.
Huh?
No.
Are there any questions?
Ah,
Yeah. Before you mentioned the idea of the time change in the generator.
what?
Before you mentioned the idea of the time change, and you were looking at the generator in terms of
Yeah.
polar coordinates, I thought that maybe the diffusion itself could have been written by absorbing the gradient of U in the diffusion in the I mean, what I was trying to do the computation, I'm not sure if but because it looks like you will get something like a gradient.
Yeah.
Or not.
Yeah, maybe it's not a surprise that you get a gradient in the end. Because
Well,
be careful,
I'm not sure,
be careful.
but but maybe
Be careful because
but,
sometimes you have a family of Markov processes which are reversible. You take a limit, at the end they are no longer reversible. So this is not a general principle. Don't ask me an example. I don't have to be careful. You will be invariant, it's true. That the invariant is more. But you still you have a strong degeneracy.
yeah, sure. But
yes, morally, maybe it's
maybe. Maybe.
Yeah,
I mean,
so it's difficult to make the complication. But yeah, maybe there is a reason we are. I don't think about.
But maybe. Yeah, I will do the computation. Any other? There was something I was confused about. So essentially, when you do the gradient ascent,
yeah,
you get into quite an explicit invariant measure for your process. If I understand right.
Yeah, but yeah, what I mean the invariant measure doesn't depend on beta is positive or negative. As long as you don't ask to be a probability. It is an invariant.
Yeah, so what I don't understand is like gradient ascent is just looking at the maximum. So why don't you get the same result?
Yeah, but no, but you are weak. Let's see where is the invariant measure. Initially. No. It's here somewhere.
And
where is the formula?
There.
Yeah. So be careful about the sign of beta because you want U, you say, when U is large, if I make an ascent, for instance, I should have more mass that the this is reflected by this power. Is it positive or negative? If it is negative, as it seems, beta and it is not, then you will put a lot of mass, small value of U. But if beta is very, very negative, you will put few mass. So that changes the descent and
okay, but I think that you always get, but still,
but
you always
it's
get
always true. Doesn't matter what
yeah.
is beta.
Okay, so what I had missed was that you are doing square root of U. So if you get into a maximum, you're going to the maximum, but you will get more fluctuations around the maximum.
Yeah.
Fluctuations around the minimum.
Yeah. And well, if you go to a maximum, the U in front of the point motion is strong, so you won't stay. Yeah, you have a lot of, but it's when you go close to the limit that you get freeze. The body motion sure anymore.
So in this one,
diffusion converges as fast as or as slow as it does with simulated annealing, or does it go faster?
First, simulated annealing doesn't converge very much short. Converge only low.
Yeah.
And here you have a convergence which is much short. But it's difficult to compare.
Yes, I agree. But somehow, if you run simulated annealing
Yeah.
for less than a lifetime, you still are fluctuating.
Yeah.
So can one expect in this equation to get a convergence in difference with simulated annealing?
Yeah. It's true. You can compare. You can consider something like the law of C. And so, for instance, mostly.
Yes, for example.
You can consider what is the speed of convergence. You can consider simulated annealing with my minimum of u0. So we didn't check that. What is going? I think that this one will be faster. Because simulated annealing is not very fast. No, you have to. It's even terribly slow. And my guess would be that make the
computation converging at a theoretical speed. You have to speed it up, and then you don't have.
Yeah, but you have explicit bound. Or if you take simulated annealing here, you can compute what is the speed of convergence.
Yeah, but
depending on
it's like a logarithm. Logarithmic. It's really.
No, it's maybe polynomial, because we have always this minus beta nu, the invariant measure, which is like that, which is exponential. It's true. The beta will be logarithmic, but here you put it in that. So if you look, you ask for the probability that u is larger than epsilon, this will be, in fact, this will be polynomial. But I think that this, my guess is that it will be polynomial in the case of simulated annealing. And but shocking is the application. Yeah,
maybe a naive question, but suppose I don't know the minimum. I just have a lower bound with some distance. I don't know, epsilon. So
but
better things in that.
But if during the process you have a process.
Yeah.
During the process, you have a bond. You start with a bad bond. You know that it's say for instance at one something. But during your process, you have more and more refined estimate on the global minima and make it evolve with time also. So you use the information to get on that. Yeah, maybe it can work. And this is the idea of this swarm algorithm. What they are doing, I have to remember. So now I remember. So normally you have several particles, and you look at the number of particles which are around you. You follow a gradient. Each one a gradient. But furthermore, they look at how many particles there are around. If there are a lot of particles, you speed your Brownian. Or if you have too few particles, you also, your Brownian motion, you push it very strong. It's only when there is a middle size of a particle around you that the Brownian motion is not so strong. Otherwise, so in practice, it means you are in the street, and there are a lot of people who try to run away every direction to get away from that. Or if there is nobody, you are afraid also. So, and this is in word the swarm algorithm. And doing that, if you look, so you will look at the evolution. Since you have particle, you will make the empirical mean of the particle in space. And this empirical mean, if maybe this empirical mean we compute because you have everywhere, and the evolution of this process, because it is non-linear, you have you can use the distribution, and the distribution see a lot of things, in particular the global minima. That's all you get an estimate of the global minima in the process. Because the process that I described to you, the particle, each particle, this is Markov. And you don't need to know where is the global minima, because I just counting how many particles there are around me, and I'm just using the gradient. So no minimal U of U. But when you look at the law of that, it follows an evolution with the PD which was written, and this one gets the information of the global minima in the limits as the times evolve. So you have a limit of the process converge to that for large time. This is the basic idea. But this is not rigorous for the moment. This is just an heuristic. What's rigorous is we prove the swarm algorithm under quite restrictive precision that it goes to the global minima. In particular, on the dimension, we only have done it on the circle, so it's who cares about the circle. And I said that because there is a functional inequality at some point. And I say, oh, we were not smart enough to compute the good functional inequality. But it seems that if you take this limit of the swarm, it shows that because of the dimension, in fact, it was a bad idea to use this swarm algorithm. Something is not good. So here it's a bad example, but we can try to imagine an algorithm trying to compute in the same time the global minima and to use that in this evolution. But this is not done. It was just an idea, and it's important.
Any other questions? Not, we can thank Laurent.